All right, so where's G end up? Show me that again. Yeah, so this is an x-axis reflection. It's going to end up in the fourth quadrant. You know, after all that, I didn't pick up the pen I dropped. So that'd be G. Note the difference. It's all in where the minus is. So where does this end up? And so it's a y-axis reflection. It'll end up in which quadrant? The second. So this would be H. Incidentally, how could I get 1 into the third quadrant? Say what? Yeah, and so if I were to reflect H across the x-axis, I'd have to slap a minus sign on the outside. So I'd have 1 on the outside and 1 on the inside. And incidentally, those two minuses wouldn't cancel, oddly enough. All right. Sounds good to me. Let's talk about stretching and shrinking. Okay. Now here's where we're going to have to, like, I want to show you some things, but due to symmetry, you're not going to be able to see the difference in them really well. So here we go. Let's say that f of x is the absolute value of x again. We already know what that looks like. So that looks like a v. There's f. Any thoughts as to what that might do? Actually does the opposite of that. This actually makes it look narrower, but that's not actually what's happening. So this looks like this. This is G. That 3 on the outside, instead of just making the graph narrower, it's actually making everything 3 times as tall as it used to be. So, like, for instance, if I get my magic pen here, make sure it's in yellow, because whenever I write in yellow, people can ignore it. So let's say that I'm using this point right here. Well, when I take 3 times the absolute value of x, that point jumps up to 3 times its original height. So essentially, I'm taking this and I'm stretching it up vertically. I'm not actually doing anything horizontally, but due to the symmetry of the graph, it appears that way. Blue. So if I have a 1/2 there, what would that do? Yeah, it's going to look wider because it's going to compress it down vertically. So that same point is going to be half as high as it was. It's going to be better if I show you a graph that doesn't have as much symmetry. In fact, let me go ahead and do that right now. So, for this one, I'm going to get a coordinate plane because I want this to be drawn fairly accurately. All right, here we go. I just made this up. We're going to call it F. All right. Now, let's say that I want to make some g of x. This g of x is going to be 2 times f of x. So what this 2 does is it takes the output of f of x and doubles it. So basically, the output would be the y. So this 2 is basically just going to double the y like we did before, except for before, because of symmetry, it looked like it was getting narrower. You'll see how this isn't getting narrower at all. So when I do g, I basically take all the y coordinates of f and I double them. So that one's going to stay put because 2 times 0 is still 0. This point's now going to be twice as tall as it was, so now I've got that. This point is going to go down twice as far. And then that point's going to stay put. So do you see how this didn't get any narrower, but it's taller? That's exactly what happened on the last graph. You just couldn't tell. So this is G. Similarly, just to keep it simple, if I did 1/2 of f, then that would shrink it down to half its original size. This stays put, that one goes there, that one goes there, and that one goes there. So this blue one is H. And now that you've got some colorful spaghetti action going on, there you have it. So let's formalize this. So this is vertical stretching or shrinking. Last semester, I may not have made you distinguish between the two because all we did was vertical stretching. But this semester, it's going to be very important to distinguish between the two. So vertical stretch / shrink. So if I have y equals c times f of x, if c is bigger than 1, then that's a stretch. If c is between 0 and 1, that's a shrink. And both of these would be by a factor of c. All right. We did vertical. Let's do horizontal. So let's see how this works. Let's draw that same graph. So That's F. So let's say I want to do g of x is f of 1/2 x. Now the way this works is that I'm cutting all the x's that I plug in half. So I would have to plug in an x that's twice as big to achieve the same output, because it would have to be chopped in half. So in order to get this point here at 0, instead of plugging in -2, I would have to plug in -4 to g because of this 1/2 x here. Because half of -4 would be -2, and that would give me the same output. So this point that I circled is going to end up right here. If I want to look at this point right here, the original input would have had to have been 1 to get that point. The new input would have to be what? Because this 1/2, what would it have to be? 2. So this point's going to go out to here. This point right here originally had an x of 3. What's its new x going to be? 6. So somewhere over here. And notice that the point that had the x of 0, half of 0 is still 0, so that's going to stay put. So this is g. So notice that g isn't any taller, it's wider. And it's twice as wide. So what do you suppose happens with this one? So this one is going to be 1/3 as wide as it used to be because of the 3 here. You remember on the last screen when I took the y coordinates and multiplied them by a scale factor when we did vertical stretching and shrinking? Here I'm essentially multiplying the x coordinates, but I'm multiplying them by the reciprocal of whatever the number is in with x. So this one's going to be 1/3 as wide. So this point here was at -2. It's going to end up at -2/3. This point was at 0. It's still going to be at 0. This point was at 1. It's going to end up at 1/3. And this point was at 3. It's going to end up at 1. So it's still just as tall as it used to be. It's not any shorter or any taller, but it is a lot narrower. So this graph is H. So I have just enough time to formally write this out. So for horizontal, stretch or shrink. Well, I wrote that in a straight line. Y equals f of cx. So note that again, horizontal happens on the inside, vertical happens on the outside. This time,